So my name is Grace Zimmerman, and this past summer I worked on the project Flux Radiometer for the ice giants at Goddard Space Flight Center. And my mentor was Dr. Shahid Aslam, and he worked within Code 693, the Planetary Systems Laboratory. So the ice giant's Flux radiometer, which we call the IG-NFR, is a potential payload on a future atmospheric entry probe to either Uranus or Neptune, which we call the ice giants. The IG-NFR will measure the upward and downward radiation flux, and it's important because it will answer two questions from the ice giant's pre-decadal survey. Those questions are, what is the planet's atmospheric heat balance, and what determines the planet's tropospheric 3D flow? The IG-NFR will answer these by telling us about the heating and the atmospheric motions within the atmospheres of an ice giant. And it will also serve as a reference for remote sensing retrievals in the future. So the IG-NFR is based off of the Galileo NFR, which was the atmospheric entry probe for Jupiter. But the IG-NFR includes extra viewing angles and a narrower field of view. The IG-NFR, the current specifications for the instrument are 7 spectral channels from 0.2 to 300 microns, and each spectral channel is measured with a Winston cone, and each Winston cone has a 10-degree field of view. IG-NFR has 5 viewing angles, has plus and minus 80 degrees, plus and minus 45 degrees, and 0 degrees, as you can see in this figure to the right, and it also has a 2-second integration time. So my part of the project this summer was focusing on Uranus, and I focused in on channel 4 of the IG-NFR. And this channel 4, its range was 12.5 to 25 microns, and it was kind of troublesome because it was prone to really large variations in radiation flux. And due to this, the signal-to-noise ratio, the SNR of the IG-NFR, is also prone to those large variations. And there's a lot of factors that contribute to the SNR, such as the integration time, the viewing angle, the solar elevation angle, and the Winston cone field of views. But channel 4 is really specific in that its SNR kind of relies on its relationship with the temperature profile of the atmospheric model. Because of that, channel 4 serves as a thermometer. And channel 4 also exists in what we call the Valley of Death, which is right in between the radiation contribution from the downwelling solar insolation and the radiation contribution from the upwelling thermal energy from the planet's interior. So it has a lot of factors that cause its variation in radiation flux. And so to explore its role as a thermometer and the effect that temperature variation has on the SNR, we use 2 radiative transfer modeling simulators, PSG and NEMESIS. So to start with, so I could really understand NEMESIS and what the program was doing better, I used the Oxford simulator. The Oxford simulator was created by Martin Roos to simulate the performance of the IG-NFR as it descends through the atmosphere of an ice giant. It runs off of spectra from NEMESIS, so pre-calculated spectra, that the Oxford simulator then puts through more calculations to determine how the IG-NFR sees the spectra. And the Oxford simulator runs off of a few important parameters, such as solar elevation angle, and so that's just the elevation of the sun off of the horizon. The NFR viewing angles, which I had mentioned in the first slide, that's just the different angles that the NFR sees through, and the noise equivalent power, or the NEP. For the IG-NFR, that's 37 picowatts. And so for all of my calculations, these are 3 constants. So the solar elevation angle is 10 degrees, the NFR viewing angle is 45 degrees, and the NEP is 37 picowatts. Now for the field of view, I did all of my calculations for 5, 10, and 15 degrees, but as my team has narrowed in on a 10-degree field of view for IG-NFR, those are going to be the main calculations I show you in this presentation. So once I could really understand the calculations that the Oxford simulator was doing on the NEMESIS data, I could then filter out the simulation itself and just write scripts that would do the same calculations straight from NEMESIS. And once I could do that, I could look at the planetary spectrum generator, or PSG. So to start with, I used pre-calculated spectra from PSG for the same model of Uranus. So I could then compare my pre-calculated spectra from NEMESIS to the pre-calculated from PSG and run it through the calculations for the IG-NFR's parameters and see the signal-to-noise ratio that I get. And here is the graph of that data. As you can see, they're pretty similar. They go through a lot of the same calculations, but they're really advanced programs, and so there are differences in certain calculations, and there's differences in scattering and layering schemes. Most of that difference can be seen here at the top of the atmosphere, but as the IG-NFR is operating mainly at 0.1 to 10 bar range, you can see those calculations are really similar there. So basically what I was doing with the PSG is really similar to what the Oxford simulator was doing with NEMESIS. But planetary spectrum generator is really interesting in the fact that the user interface is a lot more user-friendly. So by that, I mean it was a lot easier to learn and a lot easier to generate my own spectra with my own atmospheric parameters than it is, say, with NEMESIS, where it might take me a lot longer to learn how to use. So for PSG, to start with, I would upload a configuration file and then click Generate Spectra, and it would give me my spectra that I could then push into a program and calculate the SNR. But the only downside with using the browser version is that to get the nice SNR curve you can see here for every layer in the atmosphere on descent, I would have to click Generate Spectra 44 times to account for every single layer. And that gets pretty slow. And another factor is that for the upward and downward radiance, the PSG distinguishes between the two, and you have to do two separate calculations. So that's 88 calculations you have to do just to generate one of the SNR curves that will really help us with the sensitivity modeling. Because of that, I learned how to use PSG without the browser version, where I instead edited a configuration file using a Python script I created. I then sent it to the PSG API using curl commands, and then I got the spectra back and ran the calculations on that. And I created a Python script that would do that hundreds of times for all the different atmospheric parameters I was looking at. And from that, I could really start running with all the different parameters I wanted to explore with temperature variations. So the 4 different scenarios I really looked at were the hot scenario, and so that's adding 50 Kelvin, the warm scenario, which is adding 5 Kelvin, the global scenario, which is where I add the 50 or the 5 to every single layer in the atmosphere in my SNR curve, and the local scenario, where I add 50 or 5 Kelvin to just the layer I'm looking at and the ones immediately surrounding it. So you can see a representation here to the left of all of my scenarios, where you have the standard atmospheric parameters for the accepted model of Uranus, the global, where I just added 50 Kelvin to every single layer, and the local, where I just added 50 Kelvin to the immediate layer and the ones surrounding. And to the right, you can see the results of my sensitivity modeling. You can see the SNR as a function of pressure. So this is every layer in the atmosphere. And this is for the warm scenario on top and the hot scenario on bottom. And another thing you can note with these graphs is that for the upward SNR, it reaches kind of a maximum even as it continues to go out of the atmosphere. This is due to the fact that to measure that upward radiance, you're actually looking down. You're using the nadir viewing to measure the upward radiance. And so at some point, no matter how far away you get from the atmosphere of the planet, you're still viewing that top layer. So you're still getting radiance in the IG-NFR. But the downward SNR tends to go towards a 0 signal-to-noise ratio, just because to view the downward SNR, you have to look up, use the look up viewing, and then once you exit the atmosphere, at some point you don't have any more atmosphere to look at, and you're just looking into space. And so it's nice to see the science is modeled there. But as you can also tell, any variation in temperature, as all my parameters dealt with temperature, any variation in temperature here is dramatically changing the SNR of channel 4, which is to be expected if channel 4 is serving as a thermometer for us. And I also graph the differences in all of my scenarios. So the difference in local and normal, global and normal, and global and local. And I did that for the hot scenarios and the warm scenarios. So some conclusions I can make about the studies. Of course, the sensitivity modeling showed what we had hoped would happen, so that there's a very large variation in signal to noise with any change in temperature values, which really goes to show that channel 4 is serving as that good thermometer on descent. These results can hopefully be compared to future measurements taken by the IG-NFR if it is chosen as an atmospheric entry instrument. And we can look back and perhaps infer if the SNR for channel 4 is much different than expected, that maybe we need to revise the standard temperature profile we have for Uranus. And the difference in global and local variances is also really important. As you can see, for most cases, the difference in global and local, represented by this purple line, it's 0, which points to the fact that the atmosphere is so thick and opaque, where you are measuring, you can only see the layers you're immediately looking at and the one above and below. So it does not matter if we make the entire atmosphere very warm or just the layers we are immediately looking at. The atmosphere is so thick and opaque that we can only see what's immediately directly in front of us. So as I worked with PSG this summer, I got pretty comfortable with working with it, and I started on a side project towards the latter half of my internship. I started on the Myriad project, whose goal was to use an AI machine learning chip in order to fill in the gaps of knowledge in the observed atmospheric model of Venus. This chip would be potentially used on board an atmospheric entry probe for Venus. So the team started looking at the Exoplanet Generative Adversarial Network, or EXOGON, and EXOGON's an application of machine learning for atmospheric modeling of exoplanets. So we started looking at this program in hopes of doing the same atmospheric modeling with machine learning, but for Venus instead of exoplanets. And to really do that, we have to go to the root of machine learning, which is the training set it learns off of and then creates inferences from. So we needed to create a training set that was for Venus instead of exoplanets. And to start with, I created a script to generate a Venus model training set for EXOGON, and I did that using PSG because it's relatively easy to work off of scripts I had already created and just work them to instead go through however many iterations of different parameters we need to create a really whole large training set for EXOGON. And so my starting parameters, I worked with 7 molecular abundances, and I created a program where a user can come along and change the lower and upper bounds that they're looking at for each molecular abundance and go through however many or however few iterations they need to create a large or a smaller training set. And I started towards the end of my project, so I didn't get to accomplish everything I wanted to do, but the next thing I would do is explore the various viewing angles and, of course, how that changes the radiation flux it takes in. And that would really create a more advanced training set for EXOGON to use. Here are some of my references and acknowledgements I've used this summer. I want to give a special shout out to Ish Oslam for directing my internship and answering my many questions, Geronimo Villanueva for creating the PSG and teaching me how to use the program, as well as answering my many questions about how to use it, and Nico Gorius for guiding me on the PSG AI application with his Myriad project.